All right, in this video, we're going to take a look at continuity. And you've probably heard about functions being described as continuous. And up until now, we've sort of had an informal definition of continuity. A continuous function is basically one you can draw without taking your pen off the paper. Doesn't matter if it's got smooth or sharp curves, right? But things like rational functions that have vertical asymptotes are not going to be continuous because you have to pick your pen off the paper to cross an asymptote. Functions that are piecewise defined with open circles and closed circles, right? Those are going to be not continuous because you have to pick your pen off the paper, right? But picking your pen off the paper isn't exactly a very formal definition. So one of the things we're going to look at is a more formal definition. And now that we have the tool of limits, we can use this limit definition to help define what continuity is. So we're going to take a look at these three pictures here, right, that we have that give us three cases at which a function is considered to be not continuous at C. Notice that we have an open interval from A to B somewhere around C. It's not so important where A and B are, but C is clearly in the middle of that interval. And if you notice in this first graph, right, the reason we have a break in continuity is that the function itself doesn't exist at C, right? F of C is not defined. And the second graph, F of C is defined, right, because of this closed circle here. But there's a limit. The limit as x approaches C doesn't exist, right? From the right, it looks like we're heading to one y value. From the left, it looks like we're heading towards another y value. Therefore, the limit doesn't exist. Now, in this third example, f of c exists, and the limit of f of as x approaches c of f of x exists, but they don't agree. So there are three different cases at which we can become discontinuous or not continuous at a specific point C. Either the function is not defined at C, the limit doesn't exist at C, or the limit and the function exist, but they're not equal to each other, right? So we sort of have the written definitions here, and then we have the visuals above that kind of show each of those cases. Right. Here, as it's nicely summarized for us, those are telling us where we're not continuous. This is telling us what it takes to be continuous at a point. In order for a function to be continuous at C, we need all three of these criteria to be met. The function has to exist at C, the limit has to exist at C, and the function value has to match the limit value. So we're going to take a look at some of those examples. So here's a few functions that we've seen in our math career here. First of all, f of x, right? This is a polynomial function. Specifically, it's a parabola, and you might have a very good, quick understanding of what a x squared function looks like. Right? We know that a parabola opens up or down, in this case up because the coefficient of x squared is positive, and we expect this function to be continuous everywhere. There's no breaks, there's no points where the function becomes undefined, there's no points at which the limit isn't exactly the same value as the function. So we could say that f is continuous, which sometimes we abbreviate CONT, and we use interval notation. So it's continuous on the interval from negative infinity to infinity. All right. Infinity got a little small there. Let me see if I can clean that up. All right, we'll say from negative infinity to infinity. Okay. When we take a look at g of x, let's just sort of separate this over here. When you look at g of x, you might recognize this as a rational function with vertical asymptotes, and in fact, it shouldn't be shouldn't be hard to see that x cannot equal -4. That's one of the domain restrictions, and also we can see that it causes g of x to have a vertical asymptote. Now, we know that from our experience with these functions before, that every other point has a value and the function is well behaved everywhere else. So in this particular case, everywhere the function exists, it's continuous, except at -4. So we want to say, sorry, not f, g. Right, and I'm going to abbreviate g as continuous. Now, if you want to include everything except for -4, we're going to start at -infinity and go up to, but not including -4. And we're going to put that together with -4 on to infinity. Okay, so this way the open parentheses excludes -4, but everything but -4 is in there. Okay. Now, h of x is another type of function that you may or may not have familiarity with. You certainly may not be as comfortable with this. But if you look at h of x, it's a piecewise defined function. It has one rule when x is less than 2 and a different rule when x is greater than or equal to 2. Now, in this case, we have two lines. We're going to follow the line x plus 1 for all the x's greater than 2, and we're going to follow 3x minus 4 for all the x's less than or equal to 2. We've studied enough lines to know that the lines are continuous everywhere. The real question is, when you hop off of one of these lines and hop onto the other line, do you in fact have a point of discontinuity? So if you remember with your inequalities, right, x less than, greater than 2, sorry, is going to be an open circle, and x less than or equal to 2, because of the equality, is going to be a closed circle. Sometimes it erases my circle if I fill it in too much. So we have a closed circle here, right? So what we need to do is see, is the closed circle right on top of the open circle? If not, we're going to be facing the situation in the last case where the limit at x as x approaches c doesn't exist. In this case, x equals 2, right? 2 is the only issue where we might lose continuity on this function because both pieces are lines. So where is our open circle going to be? Well, technically, we never actually reached 2, but if we were to reach 2, we would be at 2 plus 1 equals 3, right? So our open circle is going to be at 2, 3. In the second case, right, we do actually reach 2. So the closed circle is going to be at 3 times 2 minus 4, which is 6 minus 4, which is 2. At 2, 2. Right? So if you were to graph these, you would have an open circle with a y-coordinate of 2, a closed circle with a y-coordinate of 2, an open circle with a y-coordinate of 3. The open and closed circles would not connect, right? They would be separate, and therefore we would have a point of discontinuity. So we would say here that h is continuous on everything up to 2 and everything from 2 on, right? Sometimes we, don't write the union symbol between it. That's fine. Technically, we probably should, but I didn't write it here. I'm not going to erase it to stick it in there. But those are the two intervals. It includes basically everything except for x equals 2. Now, when we talk about continuity, we're giving all of our answers in terms of x coordinates. We're always talking about the input value. We're not interested in the y coordinates. We don't want to know if there are y values that are skipped over. That's a different concept. So continuity is always defined based on the input variable x. We have different situations where we have points of discontinuity. If you look at this first example, the rational function 1 over x, we have a discontinuity that can't really be resolved in any way. We have a vertical asymptote. We have a situation where we have a line going like this, and then maybe another line or a curve going like this, right? Redefining f of c is not going to be able to make this function continuous. So we call this a non-removable point of discontinuity. Some functions, and we've seen functions like this already with our limit section, right? We see something that looks like a rational function, but upon further analysis, we determine that it's really just a line, right? Because it simplifies, but we still have the restriction that x can't equal 1, so we get a hole in the graph, right? Now, this function is not defined at 1. This function is not continuous. But there's another function, x plus 1, which would be this line here, right? That is continuous everywhere. And if you thought about filling that hole in by letting f g of 1 equaling 2, you could then make this a continuous function. So with one simple definition, we could fill that hole, and we call that a removable discontinuity. So in a case like this with removable and non-removable discontinuities, right, you can see here that at x equals 2, we do have the limit, right? As x approaches 2, the limit exists for f of x, and in this case, the limit would be 4. So if we define f of 2 to equal 4, we would have a removable continuity. So we have a discontinuity, removable discontinuity. Sorry, my pen is not working very well. I'll just type this. I think it'll be easier to read. A removable discontinuity at x equals 2. Okay. But if you notice what's going on here at x equals 5, right? The limit as x approaches 5 of f of x doesn't exist, right? As you're approaching from the left, you're going up towards 6, and as you're approaching from the right, you're heading towards 3, right? And there's no way to redefine f of 5 to make this function continuous. So we would say we have a non-removable discontinuity at x equals 5. This isn't a huge issue. It's not going to come up a lot this semester, but it does sort of help us understand the difference between a hole in an otherwise continuous graph versus a point at which the graphs actually separate from themselves and the limit therefore doesn't exist. Okay. So at the beginning of this section, we're talking about continuity. And for a while now, we've been sort of highlighting what's going on in a case like this, where we have these parts of the curve that don't come together. And we would certainly be able to, at this point, only have the language to say that the limit as x approaches 5 doesn't exist. But we could say a little bit more than that. We can say, if you're approaching 5, if x is approaching 5 from the right, it looks like the y values are heading towards 3. And if you're approaching 5 from the left, the y values are heading towards 5. I think I said 6 before, but this is 5. So we're going to introduce one-sided limits in the next lesson to help define two-sided limits that don't exist where the one-sided limit does exist.